So what we considered was freely moving electrons here on some lattice, to which then is added an interaction which is local. And we first diagrammatically observed that there's some instability in the transverse spin susceptibility, signaling some magnetic order. And this then motivated us to derive an effective field theory for some Hubbard-Startonovich decoupling field, which was in the exchange channel and took into account like the magnetization. So what we did is we derived the effective field theory so far and made the mean field analysis. From the mean field analysis, we found the following phase diagram. So spanned by the two parameters, temperature, and then the parameter, relevant parameters, interaction strength times density of states. And where this is 1, we have at 0 temperature phase transition, which now is a quantum phase transition because it's at 0 temperature, from some paramagnetic to a ferromagnetic phase, and at final temperature this extends then in the following way. So this is the paramagnetic phase and the ferromagnetic phase. This is what we derive from a mean field analysis. Now what one then has to do, of course, one has to see if this phase is stable against fluctuations, and this would be done by an analysis, for example, RG analysis of an effective action of fluctuations. So what we want to do here, we don't go all the way to the RG analysis, but still there's something interesting if we consider the effective theory of fluctuations. And what we are going to do now is really to derive this effective theory here around this quantum critical point. And then we will make some comments, general comments about like symmetry breaking, because what we see here is that this ferromagnetic phase is signaled by a non-trivial solution of the Sellar joint equation that we found. And this actually breaks some symmetry here, O3 symmetry, and this then leads to soft fluctuations. So we will first derive now the effective theory for fluctuations, in this case quantum fluctuations in the vicinity of the quantum critical point, and then we will make some general remarks about symmetry breaking and Goldstone modes and effective actions. Okay, but let's first go through like the general scheme that we formulated in the end. In one of the last lectures, which consisted of 5 points, and the 4th point was 7-point analysis, which led us here to this phase diagram, and the 5th and last step is then the derivation of the effective action, which here now I think I'll do in some more detail some of the calculations. I mean, you will see always appearing in a way the same elements here, because we're always considering here the electron gas, which has some interaction, so you will see structures always appearing the same way, but probably I will go into some detail that you want to see like typical kind of calculation that you have to do to derive the effective action. So the idea is that we want to complete now the first part of the lecture, step 5, which is the effective theory for fluctuations. And what we will do is here concentrate on the region close to the quantum critical point. Okay. Here, near quantum critical point. So let me just recall that this phase diagram was based on a mean field analysis of the following action that we derived after doing the usual steps, like Hubbard-Startonovich, where we decided to decouple the magnetic interaction of SZ-SZ, like spin-spin interaction, and the effective action after introducing Hubbard-Startonovich field and integrating over the electrons was just this action here, where this is a free electron Green's function. This is I omega n minus I omega n plus epsilon p minus mu, and this is the Hubbard-Startonovich field. Okay. Now what we said is that well, for the fluctuations, what we will do is we will parameterize the field by the mean field contribution, which was homogeneous and static. Okay, so only depends on the form momentum Q equals 0, and then there will be fluctuations. So what we do is we insert this ansatz here into the action, then we get well, in this, and then expand in the fluctuations. Okay, so first we get the mean field action, and then we get the fluctuating part, which we then expand in the fluctuations. And we already noticed, because we're doing here an expansion around a saddle point, there's no linear fluctuation, so it starts with quadratic order. And then due to the symmetry that we have here, m going to minus m or delta m to minus delta m, there's only even powers appearing in fluctuations. So we said that the general structure, so we insert this ansatz here, we'll then use that trace ln minus m bar sigma z minus delta m sigma z. We can use always the same trick, so we write this as a Green's function in presence of the mean field magnetization, and then make just a trace log expansion of this term. No? So we can write this here as trace log g to the minus 1 m bar minus sum over k 1 over k trace g m delta sigma z delta m to the power of k. And we said due to symmetry, so this will start, so because it's center point with k equals 2, and then there will be like the contributions that we concentrate on is this, the part in delta m squared and force. Okay, so we'll see that at some point one should also include this order, but so for now we just concentrate on the first two contributions, which is the quadratic fluctuation part and the particle. Okay, so that's what we said last time. Okay, and this is always like the generic thing. What you can do is you have to expand the trace log in fluctuations, and you can do this by separating just the mean field Green's function here, and then you have products of the Green's function times the fluctuation, which you can then expand in small fluctuations. Okay, that's always the same. So this is what we did at the end of last lecture. So this is why I just did this now very quickly, but you recall it, yeah? Okay, so I don't have to go into this. So what we do now is we consider exactly the second and the fourth part here. Okay, so the second and fourth order here, and if we are concentrating on the quantum critical region here, well, there we said we are considering here the case that we have a second order phase transition. We are going to verify that this is the case, where the magnetization here, the mean field magnetization, just builds up slowly, continuously around the quantum critical point. So if we are restricting to this region, the magnetization still is small and can be neglected. So this Green's function will be just a zero Green's function. That's what we are going to do. Okay. So near the quantum critical point, m bar is 0, and we can just for convenience call delta m again m. Yeah, it's like the same what we did for the when we looked at the density channel. Okay, so near quantum critical point. So for convenience, I mean here we look at the quantum critical point because afterwards we want to analyze the quantum critical fluctuations here. Okay, so at this point you have an interesting scenario, and later on we'll try to look at the RG, so this is like the interesting point. But then we can set m bar to 0, and we will call just delta m, we will call them for convenience. Okay, so that's the starting point. Well, let me just all this here. So we will see that m bar is more than 0. We will call delta m equal m, and for now we have to specify our system, so we will look at the 3D system with the quadratic dispersion p squared over 2m. Okay, just to do the calculations. So what we have then is the action consists of this contribution. If we go to fourth order, we will have the first contribution, which is trace 1/2, trace g0 sigma z m squared, and the fourth order, which is 1/4 trace gm sigma z m all 4. So what we will have then is the effective action here up to fourth order. We'll be just copying this over there, n over tu, q, and q, and minus q, and then we will have minus trace g0 sigma z m squared minus 1/4 trace g0 sigma z m to the power 4. Okay? Higher order terms we will not consider. Okay, so that's the usual thing. Now just let me recall that the trace here is the trace over 3 spaces. So it's, if you want to go to momentum space, then it's sum over Matsubara frequencies, sum over momenta, and sum over spin. Okay? Or sum over spin, real space, and imaginary time. Okay? So let's see. So let's consider these two terms separately. Okay? So let's first consider this term here, and just to give you like diagrammatic interpretation of this is G0 sigma Zm, G0 sigma Cm. So this corresponds to a diagram of this form, no? Where this is sigma Zm, and this is G0, G0. Okay, and this is sigma Zm. This is one diagram with two like fluctuating fields. Now this here would correspond then just, well, you have a single loop with 4 external, with 4 fluctuating fields. Okay, so this would be the 4 sigma Zm, and this is the 4 field functions. Okay, you can diagrammatically depict these contributions from the trace log as like always one loop diagrams with then fluctuating fields attached to them. Okay. So let's first concentrate on this term here. And as said, so I'll go now in some detail. Okay, let's see, because I think it's good to see this once. Which would be this diagram. So we see, since we are considering here the quantum critical point, magnetization is 0, the G0 doesn't depend on spin, then it's just a scalar field, so the sigma z and the sigma z, they just multiply to a unit matrix, so we can easily make the trace over spin, which just gives a factor of 2. Then the G0 is just diagonal in momentum in Matsubara space, so let's go to Matsubara and Matsubara and momentum space. Then we have just, it's this diagram, so the G0 P plus Q, Q enters here, or Q goes out here, G0 P, and then Q enters here. Okay? Just P. Okay, so this is just always, you can just think of it in the quickest way, or you really, look at it in detail, or you just recall that this is a diagram, and then it's clear that due to momentum structure, it is given by this form. It's clear what I mean, no? Just so again, G0P, Q enters here, G0P plus Q, Q goes out here. So then we can just rewrite this in a form that we encounter something familiar, so I introduce here n over t just for convenience, because this is just an object that we encountered already several times. So P of Q is the polarization operator. No? This is why I introduced here the minus T over n. Okay, so we encounter again our polarization operator that we already looked at several times. So on the last exercise sheet, you were asked to do here, so this is a formal momentum, to do the Matsubara frequency summation. Okay, so these functions have simple poles. That if you do the Matsubara frequency summation, you will find the 1 over n. And then just the remaining 3 momenta, and you have the Fermi distribution function. Where here Cp is a vector is defined as f from T minus 3. So the energy measured from the Fermi level and plus I omega n. Okay? I omega m, which is for Matsubara. So this is a step that we already encountered several times, and which you also were asked to do on the exercise sheet. So now we have to do the final sum of our momenta here, and this was also asked on the exercise sheet to show that. So I just recall. That, let's see, exercise was to show that P, let me just find some 1 over n, P that this was minus 0. M from Q log I omega n Q. Okay, so this was an exercise on the last sheet, and I'll comment like on how you arrived at this. However, let me just make one comment that this was a limit where you take omega m and q to 0 in a specific way, namely that omega m over 4 Fermi q is a small number, okay, and omega m is finite. Okay, so that was a specific limit in which was taken this value here. Okay, so this is then the result for P omega n q. Oh, that's right already, the form momentum going to 0, where what you actually consider is omega m over q goes to 0 and omega n is finite. Okay. So actually that's not true. What was considered here was just the limit of q going to 0 in a way. Yeah. Because you neglected q squared. So if you, to derive this, what did you do? You did linearize this dispersion epsilon p minus epsilon p plus q. You just took the linear term p minus q over n. Okay, there would be an order q squared, and this was neglected. Okay, so this was in the limit q going to 0. This was right. Now you see that this gives us a finite result. This if omega n is finite. Okay, what we still need to consider, like it's the second contribution that we didn't consider here, which is a contribution just for omega n equals to 0. Okay, if omega n is equals to 0, there's still a contribution for small q independent of omega n, which we did not consider here and which we still have to consider like in this term. Okay, so this is only a contribution where omega n is finite. Okay. So, but let's first consider this case and now consider the limit that we are interested in, like a low energy theory where we now consider omega m over 4 Fermi Q being small. Okay. So in this case, we can simplify the log here. So what we can do here is we can just divide by 4 Fermi Q. Then we have here I omega m divided by 4 Fermi Q plus 1 and I omega m divided by 4 Fermi Q minus 1. And then we can see what this log here, we can simplify this. Okay. So let me consider now the limit omega m divided by 4 Fermi Q going to 0 to simplify this further. So let's just make here a small sign calculation that divides this plus 1 I omega m 4 Fermi Q divided by minus 1 plus I omega m 4 Fermi Q. Okay, so in this limit omega m 4 Fermi Q to 0, this is just a small, an infinitesimal imaginary increment which is on the positive half plane for omega n being positive and on the negative for omega n being negative, it is on the opposite side. Okay, so let me just write this, what I said symbolically, because I think then it's easier to see what is going on. Let's just call I0, like in this limit going to 0, and then we have a sine of n divided by minus I plus I0 sine of n. Okay, and this is important because of the analytic structure of the log. Because if we take this completely 0, we have the log of minus 1. Okay, then we have a problem. So we have to shift this a bit in the complex plane, and then we have to see if this is I pi or minus I pi. Okay? So I'll try to explain this to you. Okay, up to here. Is this clear up to here, like what happens? So this is a general term that you derive for q going to 0. Now we are interested in this limit for the effective action. We just made one symbolic simplification here. Okay. So let's consider this log careful. So we have here the complex plane, real part, imaginary part, and what we have is the log of 1. Let's consider m being larger than 0. For m larger than 0, we have the log. Let's write this as a difference of two log. I mean, you know that this is a difference of this log and this log. Okay. So the log has a problem. Well, it has a cut for negative values. So we could say that minus 1 is just e to the I pi, so the log of minus 1, like symbolically, is I pi, but it could be equally minus I pi. Okay, so we have to decide which is the sign. And how to do it is because the term that we have is not log of minus 1, but we have a small shift. Okay, so if we take m larger than 0, we have in the numerator we have the log of -1 slightly shifted up here, and the log of 1 slightly shifted up here. Okay? So we have the log of this value minus the log of this value. Okay? Now, to calculate the difference of these two logs, we have to take the log from the same sheet, no? So we have to take the log, like we cannot cross any singularity. Okay? So we have to take this log and take the analytical continuation to this. And this means that this log of -1 slightly shifted up to here in the limit of plus I0 is just the log of e to the I pi, because this is the one we connect here. Okay, so this is just I pi. Okay? And then we subtract the log of 1, which is just 0. Okay? So for m larger than 0, this is just I pi. Okay? This is just I pi, and this is just 0, so we subtract this, and we get that this is minus I pi if m is larger than 0. Okay, so this here is I pi, but we divide this by this, so we take the difference of the log, 0 minus the log of I pi, so this is minus I pi. Now if we take m being smaller than 0, well, then we have here in the denominator the one shifted a little bit below here, but it doesn't play any role because we don't have any cut here, but we have at -1, we now have the value -1 shifted on the below plane. So now we have to take again the log from the same sheet, so it cannot be the I pi, because the I pi would mean to get here we would have to cut through the cross and cut, which is not allowed. So what we have to take the log from this sheet. So this here would be the log ln of -1 minus I0, which is the ln of e to the minus I pi. So this is minus I pi. Okay? So it was important to take into account this small increment. So for m smaller than 0, we then have ln of 1 minus ln of e to the minus I pi, which is 0 minus I pi, so it's I pi. Okay, so we find that this here will just give us an I pi minus, so in the limit of omega n over v Fermi divided by 0, this will just give us an I pi minus I pi signum m. Okay, I don't have to write it. See, it's here, no? Sorry for the mess here. So we can write this as minus I pi signum of m. So positive for positive m's and negative for negative m's. The signum or signum of m. Okay? So now if we use this, we can see that in this limit here, we multiply this with minus I pi and the signum of m, so this gives just an absolute value of omega m. Okay, divided by v cubed. So in this limit here, can I write it here? So in this limit, we find this is minus μ0 pi omega m divided by v Fermi cubed. Okay? So that's just once looking carefully here at the structure of the log. Was this clear? Yeah? Yeah? Okay. Okay, so we figured out the one contribution which comes for omega m not equals to 0 to this here. Yeah? So this is one contribution from the exercise.
Esse termo não é igual ao de cima. Não devia ter um log de alguma coisa que você meio que autorizou?
Não, o que eu fiz aqui, eu dividi por V Fermi Q. So here we have isso vira uma 1 e ômega m dividido por Form Q. Então é esse aqui. Agora o que eu só queria fazer aqui é escrever simbolicamente o que isso vira no limite ômega m sobre Form Q para zero. Aí isso aqui é um número pequeno. Por isso eu escrevi isso agora como I, 0. Como...
Sim, mas para chegar de cima você teria como um fator multiplicativo de 1 sobre Q.
Não, o que a gente viu que esse logaritmo é simplesmente minus IP signum m. Então esse logaritmo vira minus I signum m, eu multiplico isso com isso. Então isso vai virar menos no zero, absolute value of omega m divided by Form Q. Porque isso simplesmente vira um número, tá? Mas um número que depende do signo do m. Faz isso sem absolute value. Tá? E só para... Isso vai entrar aqui como o propagador quadrático. É claro que tem que ser um absolute value of m, porque senão seria um boundary term que simplesmente desapareceria. Tá? Isso, na verdade, descreve dissipação. Tá? Ômega m absoluto é sempre termo de dissipação. Só falei uma vez agora para falar. Quer dizer que tem dissipação aí. No propagador. Mas o que fizemos? A gente estudou um limite omega m, so we looked at omega m not equals to 0. Now if omega m is 0, we see immediately, well, this here is just 0, okay? But we can suspect that there should be also a contribution for omega m equals to 0. So what we did here to go from here to here, we linearized the spectrum and then considered the leading order term. But there should be higher order terms for omega m equals to 0, which is dependent on Q. So these we still have to figure out. Okay, so that's now the second part we look at. This would be the propagator in this limit for finite omega m, but let's look now at the propagator at omega m equals to 0 and go beyond the approximation that we did here to figure out the finite Q contributions that were neglected. Okay, so that's the second contribution we should look at. Here. So this is, let's say, first contribution where omega n is not equal to 0. Now let's look at the second contribution. Where this is 0 and Q is small but finite. So let's look at the propagator given here, 1 over n, so I'll just copy this. In this limit we have minus 1 over n, sum over p, and I'll just work here the order because it's not convenient. And what we now have to do is, well, we have to be more, keeping more terms than we did here. Okay? So again, we linearize the spectrum, but now we keep a higher order term. So what we now write is so we keep the Q squared over 2m. And then what we are going to do is to expand the Fermi distribution as we did there. Okay, so the Fermi distribution at Q minus P is just the derivative of the Fermi distribution then evaluated at PQ over M. That's what we did here. We just took the derivative of the Fermi distribution with the term with the leading term, but now we should keep the second order term, the next leading term, the Q squared over 2M. Okay. And then what we should do is we should also, if we take here, like the next leading order term, which is small n q, we should also consider contributions from higher orders in the derivative, because there can be like second order and third order derivatives which are of the same order, where we only take, so let me be more clear. What we did here, we expanded the Fermi distribution function, and we have two contributions. One is the leading order term, because P is of the order of P Fermi, and Q is of the order of temperature. Okay, so this is smaller by E Fermi divided by T divided by E Fermi. But now if we keep this small contribution here, we could also consider a second derivative of the Fermi distribution function, where this then appears as a square, or the third order in power of 3. Okay, and it turns out that this third derivative with power of 3 is of the same order as this here. Okay, so we should not only keep this one here, but we should then keep 1/2 n Fermi. So this second derivative, P times Q over m squared plus 1/3 faculty n Fermi, third derivative, P times Q over m to the power of 3, and so on. Okay? But it turns out that these two orders are the same. Up to here clear, or? So then we just insert these two approximations here, and yeah, let's see if I go through all of the details. So let me just maybe recall how we arrived here. So here was, if you insert just the leading order term, you keep here the P times Q over M, and you have here the linearized term. So the P times Q just cancels out. The derivative of the Fermi distribution function, the temperature law to T⁴ is just the delta function. Okay, so you write here the delta function, just, and you convert then the momentum summation into an integral with the density of states, and this then gives the density of states at the Fermi level, which is just actually, yeah, sorry, there had been one minus here. That would be just one here. Okay? So there's still here a 1 minus u0, so I didn't keep it. Okay? So now what you do here, well, there is now contributions. I should have kept here the q squared over 2m. There's now contributions, just one example. If you look at this one here, in the power, that's the simplest, the third derivative, there you have pq over mq. So keeping here the leading order, 1p over qm just cancels out, and you have the third derivative with a p times q squared. Okay? And then you just use again that this is now the second derivative of a delta function. So the second derivative of a delta function can now understand as doing the partial integration to keep, to push the derivative to the other side. So let me just consider this one contribution in detail, and then so from this term here, okay, if we insert this here in leading order, one example, we have 1 over n, we have p, we have here let me write this third derivative of the Fermi distribution function. We have a p times q over n to the power of 3, and here concentrating on the leading term, this is p times q over m. I mean, there would be a q squared plus q squared over 2m, but this can be expanded and then gives terms to higher orders which can be neglected. Okay? So this would be the contribution, for example, from this one here. So it's mostly restricted. So we can see that, well, we can just cancel one factor against this, so we get a minus 1 over n, sum over p. Then we have here the third derivative of the Fermi distribution function times the p q squared over m squared. Okay? So this now we can write in the following way. So first, we notice that we have here an integral over p times q squared. Okay, let me just give you one thing that one always uses. So I just discussed this in detail to show like some things that always appear like hit a lot. This is one thing where one had to keep in mind like the complex structure. Now here's something that also always you will encounter. So we have the sum over p. This is completely isotropic. Okay, so this only depends on p squared. This depends on the direction, on px, py. So let me just write this explicitly. So this is pi, qi, pj, qj, where you have sum over I and j implicit. Okay. Now, what does this give if I just reorder the terms pi, pj, qi, qj? So this doesn't depend on p, and it's just outside. Now, if I is not equals to j, this is just 0. Okay? If you have an integral d3p, px, py, this is just 0 because of symmetry px minus x. Okay? So this only contributes if I equals j. Okay? Now, if I equals j, this would be, for example, px squared, or py squared, or pz squared. If all of the remaining here, this function depends only on the modulus of p. If this is completely isotropic, it will give you the same value for px squared, py squared, pz squared will all give the same value. So let's use this trick and write this as 1/3 p squared, which would now summing out all the 3, because then we have something invariant again, and then we have delta I jot qi squared to qi dot, where summation over repeating this is implicit. Okay? So this is just using the symmetries. Okay? So we can always symmetrize this, noting that, well, this will set this to then a q squared, and we get a 1 over 3. Okay? So let's use this trick here. So we have 1 over n, then we have the p, we have a, let's already write this as a del cp squared delta epsilon p minus mu. This derivative acts here. This one is here. And then we said we can write this as a p squared times q squared over 3m squared. Okay? So this is using this trick here. This is nothing but q squared. Okay, so now what did we achieve? Now this is all depends only on, this here is nothing but epsilon p times 2 divided by m. So this only depends on the energy, so let's convert the momentum summation to an energy integral by introducing the density of states. Okay, so let's recall that the density of states at an energy epsilon is, well, what we introduce here is the density of states per site and per spin. Epsilon p times epsilon. Okay, so this is the definition of the density of states per site, because we divide it by 1 over n, and per spin, okay, because we already factored out the spin. So if we do this, then what we get here, the minus just cancels, we have a 1 over n, we convert this into an integral d epsilon, we have a nu of epsilon. This here is 2 divided by m epsilon times q squared, so we can just put out the q squared out, that's right, q So this is after introducing the density of states. We have this here, and we have, sorry, forgot the second derivative, delta epsilon squared dx. Okay? Sorry. Mu of epsilon delta epsilon squared delta function. And let's put out the q squared here. Okay? Just putting in here the definition of the density of states. Okay? And I forgot the factor of 3. So now what we can do is just recall the density of states. The density of states for the quadratic dispersion in 3 dimensions goes as the square root of the energy. Okay? So we can write, just to simplify this a bit more and to introduce the density of states, the nu0 here was the density of states at the Fermi level. Okay? So we can write in 3D with quadratic dispersion, we can write the density of states as the density of states at the Fermi energy, and then just use the scaling of the energy with the square root. Okay? So we can just rewrite this as form. Okay, so if we now insert this here, then we can pull out the factor nu0. You can pull out this constant 2 over 3m. We have here then a square root epsilon, so we have an epsilon to the 3/2, and we can just do partial integration twice. Okay? Boundary terms do not contribute because of the delta function here. So twice partial integration, then we have a second derivative of epsilon to the 3/2, so this will give a factor 3/2, this will cancel the 3, and then a 1/2. So there's some prefactors appearing, but everything will be proportional to nu0, q squared. Oh, the 1 over n disappeared here, sorry for that, because of the definition of limits of states, and some n. So let me just then write the final result. What you get there is, okay, where do I have it? Okay, now I calculate it all at the same time, so. Okay, now I have to identify which one was which. Okay, I cannot separate. Okay, I just tell you like this. Calculation to bring it to the end, I think it's clear how to do it. There's a second contribution. So what we considered was this contribution here. So there's a second contribution. This term here just vanishes due to symmetries. You can convince it to yourself. So if you look at this contribution, insert again the derivative here, and then you see that this here exactly cancels by the denominator. Okay? So there's a second contribution which depends on just the derivative. Okay? So if you add those two contributions, I can tell you what you arrive at, and this is minus nu0 over 12 q squared divided by p Fermi squared. This is, if you look here, this doesn't contribute, and if you just take into account also this term here. Okay? Now, where does the p Fermi squared come from? You see from the density of states, there appears so there appears here the combination of chemical potential mu times m, which gives you p Fermi squared, 1 over p Fermi squared times 2. Okay? So this is the final result. I don't know if this is explained good. Okay. What I just wanted to show, so you can go through this calculation. The only thing that I wanted to show actually here was, I don't know if you knew this, like how to symmetrize this, like it's 1/3. Did you know this? Probably you know this. No? You did? Okay, so then it's good that you saw it. So that's like how you always can simplify these expressions. You want to convert the sum of a momentum into an energy integral by using the density of states, and you can always use here the symmetrization. Okay? So you get this term. Now, summarizing everything, I'll just write down the final result for the second order of the trace log expansion. So we have one contribution for finite omega, which was this contribution here. And now we have another contribution which is plus q squared. So I can actually just end here, or actually minus. So minus 1/12 q squared over q squared. So this is the final result for the contribution with finite omega m, and with omega m equals to 0, we have the q squared contribution. Okay? Let me just write the result for the second order here. See? Trace 0 sigma gm squared with factor 1/2, which comes to the trace log expansion. This is minus n over t, sum over q, 0, 0 t, minus q, q, minus q squared over 12 q squared, m of q, m of minus q. Okay, so that was one contribution that we have. This we have to add to the quadratic action of m of q, which depends on u, on the interaction strength, and then we should look at the fourth order contribution, okay, from the trace log expansion. Questions up to here? So, sorry, I don't know if this was understandable, but you have to go maybe through it once, like quietly, but there's like two things maybe you should see. This is one of the evaluation of the log, and then the one with the q equals. So then let's look at the fourth order contribution that we still have to add. So,
Esse é um termo mudança que vai entrar
no propagador quadrático
desse campo M.
Exatamente. So, if you like, we can already write the quadratic propagator. So the fourth order will give like the self-interaction. So let's write with this the quadratic propagator. So we can push out factor t. Then we have sum over q. And then we also see why we should keep the fourth order term. Plus q squared squared plus p over q q m of q minus q. So this is what we get for the quadratic propagator, where we took this into account, and then the first term, which was the 1 over u, which we had from the Hubbard-Stratton-Rich decoupling. Okay, so this is the Gaussian propagator. Okay, so this is everything that we have here in this Gaussian propagator. Okay, so now we can already see something interesting in here. And this is, what do we have? Well, we have a term which is just like a gradient m squared, like the usual gradient m squared. This is like peculiar because we are making expansion close to a quantum critical point, but it has derivatives also. And then we have a term, like if you look at the constant configuration, these two are just zero. Then we have here the mass term, okay, so the mass. And this is 1 over u mu 0 minus 1. So if u times mu 0 is smaller than 1, this is a positive, so we have a positive mass. E to the minus s squared is well behaved, so we have for large m, this is damped because we have a positive mass. But then we see, like once mu times mu 0 becomes larger than 1, where we know that we enter the ferromagnetic phase, we build up here negative mass. Okay? So this, the quadratic zero would be just unstable, okay? Just because it would blow up. So what we need now is to include the quartic terms, which will then make everything again well defined, because what we should find is that the quartic term will then come with like a positive constant, which will make the negative mass m squared in here compensate for this. So what is the problem here? If this is negative and we look at constant configurations, we see that the larger m is, the more favorable they are, because this is not suppressed anymore, so this integral will blow up. However, if there is now a term m, let's say to the power of 4, with some positive alpha, this will make everything well defined again, because this will then compensate for this term, because if m becomes large, the m4 simply will always gain against m squared. Okay, and even if this mass is negative, this will make everything well defined again. Okay, so what is the problem here? Actually, this is what I wanted to draw in the end, but we can already look at this. So, if we look at the constant configurations, S of n, okay, then we see that, well, if u mu 0 is smaller than 1, this action is just m squared, where let's call it alpha, m squared, where alpha is larger than 0. So this is just a parabola, which means that large fluctuations are just suppressed. Okay, so what is the problem? If mu times mu 0 becomes larger than 1, the mass here will invert, and we will get a S being proportional to alpha tilde m squared, where alpha tilde is smaller than 0. Okay? So the constant fluctuations would have a negative mass, meaning that the large m absolute value will be actually favorable, so everything will just explode. Okay? So what then heals everything is if you look at the fourth order contribution, okay, and this will what we will look at if you get here beta times m to the 4, and beta is positive, this will make that the action or the potential and large m will always gain and make everything stable again. Okay, and what you then see is actually that the action for constant configurations has some minimum value which is not equal to 0. This is the mean field solution that we found. This is one that breaks it's a solution of the non-trivial solution. So I'll explain this in more detail. But the point here is that keeping the fourth order term is important once we are beyond the critical value, because this then guarantees stability of the integral if the constant here is positive. Okay? So if the constant here is positive, we see that you continuous change from a configuration of this, then if alpha, if this constant is just 0, this will become very flat here, and then if it's negative, you build up these minima here. So you have a continuous change from mean fields, like the minimal action solutions which have value 0 to one with finite values. Okay, your continuous change. Now this is all guaranteed by the fourth order term being positive. So this is when you have a second order phase condition. Now it can be that this is also negative, and then you have to take into account the sixth order, which will make then everything well defined. But then it can be that the mean field solution do not change continuously from 0 to finite value, but just jump. Okay? So if this turns out to be negative, then it can actually be that you don't have a second but a first order phase condition. Okay? So this is our assumption was, well, we have a second order phase condition where we should verify that this here is a positive constant. Do you know all, I mean, do you learn this in statistics, like phase second, first or second phase transitions? Yeah?
No.
Huh? No?
Estatística não.
But so where did you learn this?
Eu já vi isso em altas energias, porque potencial, para mim, isso é basicamente um Φ4.
Do you learn Ginzburg-Landau theories? Like the effective, like what we're doing here is deriving effective theories, like type Ginzburg-Landau type, which you can also introduce just phenomenologically, and which is like typically do exactly this kind of analysis to see if you have a second or first order or phase condition. But you, okay. Okay, so then we'll do this in some more deep. So if we continue, then I make some introduction to this, like that. But is this more or less clear? Okay, so up to now we only found here the quadratic action, and we see in this quadratic action exactly reflected what we found from our mean field analysis that once this here becomes larger than 1, something interesting is happening. So in the effective theory, the quadratic term becomes a negative mass, and we have to take into account the fourth order to make this stable. And this is why we look at now the fourth order term, which was proportional to G0 sigma 0 and to the power 4. Okay, and again I just go here into detail just to show you once like how you can make this calculation. So again, it's maybe kind of stupid to present too much details. I hope it's understandable, just that you get the idea how to do the calculation. So the first thing again, we can do the sum over spin, which gives a factor of 2, because it's trivial. And then it's convenient because this Green's function is diagonal in momentum space. Let's go to a momentum space representation. So let me just write the final result after momentum space representation. So this will be G0 P1 P Q1 Q2 Q3 G0 So, if you want, you can go through, the Fourier transform, but you can also just, keep again in mind that you have this kind of diagram. Okay, so then you can just start out from Green's function G0 at P. Here comes in, let's say, some momentum Q1, which is given by M of Q1, so this will be P plus Q1. Here comes in some momentum Q2, so this is P plus Q1 plus Q2. Here comes in some momentum Q3, so this is G0 Q1 plus Q2 plus Q3, and due to momentum conservation, this momentum Q1, Q2, Q3 then has to go out here. So this is why here is minus Q1, Q2, okay? just from the diagram you can okay? So now, having said this, what we are interested in here. So this is now, I mean, this would be complicated. This is 4 momentum. We should do the analytical, like the Matsubara frequency summation, everything. But in the end, what we see, we have here the quadratic theory, which already has a propagator. The quartic term that we're considering here is only relevant to make this integral convergent. So the small q dependencies are not really relevant because we have them already from the quadratic propagator. So what we need to have here is actually only the constant contribution. Okay? So we can neglect that we are considering here the Green's function at slightly different momenta, because we are not interested in the q dependence, but only in the constant. So we can, for our purposes, write this as a p. Then take here always the same Green's function, so this would be the Green's function to the power 4. And then we have here still the q1, q2, q3, and let me just write this like in a more symmetric way, copying this q1, q2, q3, q4. So I just want to write this in a symmetric way, so then I have here momentum conservation q1 plus q2 plus q3 plus q4 is 0. Okay? So all we need to calculate is the 4th power of this Green's function. Now this will give us some constant, and then if we make the Fourier transform back of this, we will see that this gives us just a local term in space and time. Okay, and this will just then define the constant. Okay, so what we have to look at is this product of the 4 Green's functions. And let's make here, let's write this explicitly. So this contains a Matsubara sum, epsilon n. Let's write it in different order. P momentum, epsilon n, e to the I, omega n minus Cp to the power of f. Okay? This is just inserting what we have. Now, this I can just write as acting 3 times with a derivative on one such a term, no? So I can write this as P, so 3 times epsilon n omega n minus Cp, and then I have to compensate for the factor 6 and generate on this. Okay? So now this is already much simpler, but what I have here now is again, I mean, just the sum of I omega n minus Cp, which would be divergent. So I somehow have to regularize this. Okay? So what I can just do, I mean, from the exercise that you already had, you can add the term I omega n delta. Yeah? Now you can ask, why should I add I omega n? And delta I could also add minus I omega n delta. The statement is that you should find that this doesn't depend on how you regularize it. It's quite modified. So let's consider this form here. Okay? Just, I mean, we made some tricks. We know that this expression here is well defined. So we made here a simplification. Now, we could have entered here the I omega n delta. So in the limit delta, this doesn't make any change, and then we could have made this. Okay? So this is all fine. And we keep in mind that delta is to 0. Okay? So let's consider this term here. This gives a what? Minus t over 2 pi I dz. 1 over z minus Cp. Then we have here, well, let's consider this and the Fermi distribution. T plus 1 over this here now, delta, was introduced to guarantee the convergence of the negative. So we just have a simple pole, okay? So this gives minus t, and then we have the Fermi distribution evaluated at, okay? Now if we would have taken the opposite sign here, you can convince yourself, well, that it gets the same. Yeah? That's maybe an exercise that you want to do. Okay, so this is, actually it doesn't get the same here, but once it takes the derivative, then it gets the same. So you get a 1 minus NF or something. The 1 drops out once you take the derivative here. Okay? So now what we have to do is just take the derivative and just do the same thing. So the derivative here gives like the second derivative of a delta function. We convert the momentum into an energy integral, the density of states, to partial integration, and get then the second derivative of the density of states. Yeah? Okay? So let me just write down here, after this has been done, we just do again the same things. No? So again, third derivative gives the second derivative of the delta function, convert this momentum into an energy integral, a density of states appears, through partial integration, there should be the second derivative of the density of states at the Fermi level. And if you go through everything, yeah?
Não deveria ser positivo aí esse resultado, não?
Aqui deveria ser positivo, sim. Because you pick the pole in the mathematically opposite. Exactly. So then you get a minus because this is like the minus delta function, 2 times the partial integration, and the minus stays because the partial integration only changes the sign. So you get for everything in minus n over 6t, second derivative of this. So the n is because we introduce the density of states as the density of states per sign. So this is compensated here, and the t here should be 1 over t, no? Yes. 1 over t. 1 over t. The counting function is 1 over t. Okay, and the 1/6 is 1/6 there. Okay? So if we put in this here and then do the Fourier transform back here, we get a local term in real space, so this becomes then a minus n over 3t. 3t tau I m I tau to the power 4. Okay, so this is just converting this here back to real space imaginary time, and this is okay. So adding this to the action, we end up with the effective action on this sum of. So let me write here the effective action that we get in the end. We have to multiply this with a factor 1/4, no? Because it was 1/4 trace G0 blah blah to the 12. So this will give a factor 1/12. So we have a minus second derivative of the density of 12. Mi tau power 4. Okay? So this is the end result for the effective action to fourth order. And let's just verify that if we have a dispersion epsilon p being p squared over 2m in 3D, the density of states and energy epsilon is the density of states at the Fermi level times the square root over mean, or Fermi level at t equals 0. So if we take the second derivative, this will be indeed negative. Okay, so this means that this is positive and everything is fine. Okay? In 3D and for this dispersion. Okay? Okay, maybe let's do 5 minutes or less, like 3 minutes break, then I